Okay, so in this video, we're going to define what is the norm of a vector. Okay, so the norm of a vector, use this notation here, is defined as the square root of the sum, it goes from 1 to m, of u sub I squared. All right, now in terms of in R2 and R3, this is our standard Pythagorean distance, right? Where we have u1 and u2, right? If the vector u consisted of u1, u2, right? Then the norm of u here, or the length of u, right, would be here for this one, the sum of the square of its components, right? u1 squared plus u2 squared, right? Where u1, u2, those are the the real value components of the vector u. Okay, so again, this norm is not just defined for R2, R3 vectors. This vector u can be for any Euclidean n space. U is just an element of R to the n. All right, and if we notice here, right, this operation is one that we saw in the previous video. This I goes on the outside, excuse me. Okay, so we could see here that, well, that is just the dot product of the vector u itself, right? So we can define the norm squared to be the inner product of u with the vector u itself. Okay? All right. Now, one thing to realize here, that while the inner product, right, can be positive, negative, or zero, right? Since we are multiplying or taking the inner product with the variable, with the vector u itself, so this is going to be greater than or equal to 0. All right, as we can see from the root, right? And then when you multiply each vector with itself, they're all positive. That's great, right? That's always going to be positive. But when you have positive or negative, right, those negative numbers get multiplied with themselves, so they go back to being positive. So it's greater than or equal to 0, and it's 0 if and only if, right? So an equivalence relation here, equal to the number 0 if and only if the vector u is the 0 vector. Okay, so the norm is well defined, right? And it's always a non-negative real number. All right. So we're going to use this concept of a norm to develop a process of normalizing a vector. Now, first, before we get into that, let's define first what a unit vector is. Right? A unit vector satisfies so where the norm of u is 1, right, or the length of 1. All right, now I can redefine any vector once I know what if the norm is not 1, I can redefine it in such a way that we have W to be equal to that vector U divided by its norm. Okay. Okay, and now this is going to be a unit vector, right? In other words, the norm of W will be equal to 1 always when you redefine it that way. All right, and let's find out why that has to be the case, right? So here we would say that that is the square root of the inner product of W and W. All right, but W I define as some vector U divided by its norm. Okay, now here, sorry, here my handwriting's a little, not a little, it's kind of awful. Okay, and using the properties of the inner product here. And remember that norm of U is a scalar, right? So that's just a number, it's not a vector. The vector here is just the U in the numerator. So I can rewrite this. Again, this is all just properties of the inner product. All right, so I can essentially factor it out of that first position. All right, but it's also commutative for real numbers. So I can change the order here of the inner product. And then I can factor out that scalar again. And now we have two factors here. So we got 1 over norm of U squared, and then the inner product of U itself. But we said that was just the norm of U squared, this one right here. So we get 1 times norm of U squared, all under the square root, but here this is just root of 1, which is 1, and then just bringing down W. And we can see how, with using the properties of the inner product, why constructing a vector in such a way will always lead us to a unit vector. Okay, we'll use this idea of normalizing a vector at the end of this section when we introduce something called the Gram-Schmidt process, right? Where we are just not only gonna normalize vectors, but we're gonna orthogonalize them as well. We'll get more into that into the next video here, right? But for now here, our goal here is to compute the norm of a vector and state the relationship between the norm and the inner product, which we have done here, right? Being that the inner product of U and U is the norm squared. Okay, so let's try an example here. All right, so here, so I want to normalize the vector U equals 1, negative 1, 2, negative 3, 2. Okay, so most likely any vector you're given probably will not have a length of 1. So that's okay here. So we'll start off by just finding the norm of it. So the norm of u, oops, fine as the square root of 1 squared plus negative 1 squared plus 2 squared plus negative 3 squared plus 2 squared. So that gives me 1 plus 1 plus 4 plus 9 plus 4. Okay, so we get square root of 19. All right, so again, not of length 1, but that's okay. I'll redefine a new vector, w, to be 1 over root 19 of 1, negative 1, 2, negative 3, 2. All right, and again, it's a scalar multiple of vector, so the way we do that is 1 root 19, negative 1 over root 19, 2 over root 19, negative 3 over root 19, and 2 over root 19. And again, what this process does is it guarantees, and you can verify it, right, that this is in fact of length 1, right? So we can just double check our work here. And we get the norm of w. So we'll take each individual one. So we get 1 over root 19 squared plus negative 1 over root 19 squared. Hold on, I gotta plug in here. Okay. Two over root 19 squared plus negative 3 over root 19 squared plus 2 over root 19 squared. Simplifying. See, we get 1 19, 1 19th plus 4 19th plus 9 19, and we could see how, right, doing it in this way yields us with the desired result. Right, so here they'll have a common denominator, and we get 1, that's 2, 6, 15 plus 4, 19, or simply 1. Okay, so that is how we calculate the norm and how we use the norm to normalize any vector.